Hi everyone, it's Wednesday, which means it's time for another live stream from Chem Help ASAP. Now I know that many of you are in the midst of exams or midterms, so I thought we would tackle a little bit more difficult problem in terms of acids and bases. So we're going to do a titration of a weak acid with a strong base, and we're going to calculate pH at several points along the titration curve so we can see how the pH changes and how, especially at the equivalence point, the pH is maybe not what you would expect it to be. It's not the same as if you have a strong acid and a strong base. We are going to be working through a lot of calculations. We will be doing quadratic equation. If you have any questions, please just post them in the chat and I will try to answer them as best I can, and I'll also try and monitor the chat a little bit better. Okay, with that being said, let's jump into our titration problem. Okay, so if you watched the live stream from last week, this was a question that I was hoping to get to, but of course I bit off more than I could chew and I couldn't get through all of those questions. So this week we are just going to focus on this titration problem because it is a little bit more difficult, and again we're going to hit several points along the titration curve. So let's just read through the question. What is the pH of a 15 milliliter aliquot, that just means sample, of 0.2 molar nitrous acid? What is the pH after 5 milliliters of 0.3 molar potassium hydroxide is added? What is the pH after 5 milliliters more of potassium hydroxide is added? That means you've added 10 milliliters total. And then again, what is the pH after 5 milliliters more potassium hydroxide is added? And so then we've added 15 milliliters of potassium hydroxide. And we have the Ka of nitrous acid is 4 times 10 to the negative fourth. So we're going to do 4 points along the titration curve. First, when no base is added, then when 5 milliliters of base is added, then when 10 milliliters of base is added, and then when 15 milliliters of base is added. So we just want to monitor how the pH is going to change along all those points. And just spoiler alert, because we're adding base, our pH is slowly going to increase. So I'm going to try to do one of these points on the curve per page. But you know, of course, if I need more space, then I'll just go to another page. Okay, so let's start with our first point. I'm actually just going to go ahead and call this point number 1. This is when no potassium hydroxide is added. So at this point, all we have is our sample of nitrous acid. Now this is a weak acid. So at this point, we're just doing a weak acid problem, and that is it. Now nitrous acid right here, this is a weak acid. This is why we have a Ka for nitrous acid. So it is going to be an equilibrium problem. It's not going to be just a stoichiometry problem. And this is, of course, an aqueous solution. So what I want to do first is I want to actually write my equilibrium equation. So we have nitrous acid, that's an O, it's in water, it's in equilibrium, and it's going to give me hydronium and nitrite. Okay, so when working these weak acid problems, we are going to use the concentration of our acid, which is given to us in our problem right here. So you can use moles, but you just need to remember to convert that back into concentration when you're ready to plug into the expression for Ka. I just like to, if I can, and we'll have, in this case, we can start with concentration, but we'll see in later cases we need to actually go moles and then switch back to concentration. So I'm just going to start with the concentration of my weak acid, and that is 0.2. Of course, I don't have any of my hydronium ion or my nitrite. That's 0. I'm going to use up some of my nitrous acid, and I'm going to form some of my hydronium ion and some of my nitrite ion. Okay, so this is, I should be specific here. I am setting up my rice table. Reaction, initial, consumed, and now I'm getting ready to do equilibrium where I'm just adding down the column. So this is 0.20 minus x. And of course, these are both just x. If you want to write 0 plus x, it's totally fine. Okay, so now I'm going to get my expression for Ka. And this, of course, is just products, or concentration of products over the concentration of the reactants. So this is where, if you had converted to moles, you would need to come back to concentration. And we're going to go HNO2 here. Now remember, your concentration of water has been folded into that value for Ka, which is why it does not appear in the denominator. Okay, so let's keep plugging in. I have a value for Ka that is 4.0 times 10 to the negative fourth. Of course, both of these are x, so we have x times x over 0.20 minus x. Again, I'm just plugging in this expression right here. And now I need to solve for x. Well, what I would like to do is I would like to simplify my denominator right here and drop that minus x, because that's going to save me having to use a quadratic equation. But I have to test that first. So I'm going to switch colors. I'm going to do a little side calculation to see if maybe I can drop that minus x. So to do that, I'm going to take my initial concentration of nitrous acid over my Ka, and if this is greater than 500, then I should be okay to do my simplification step. Okay, so my initial concentration was 0.2. My Ka, of course, is 4.0 times 10 to the negative fourth. Hopefully this is greater than 500. And when I plug this in, I actually get 500 exactly. So my expression of 500 is greater than 500 is not correct. So this is a no, that is incorrect, which means I need to use my quadratic equation to proceed to solve for x with my Ka expression. Okay, so I'm going to show you a little bit of algebra just to get the quadratic, and then I'll show you what I do next. Okay, so the first thing I'm going to do is I'm going to take this denominator and I am going to switch it over to the left-hand side. And that's going to turn the left-hand side into this expression, 0.20 minus x. Of course, my numerator just simplifies to x squared. So next, I want to distribute my 4 times 10 to the negative fourth. So I'm going to multiply by 0.2. What is that? That is 8.0 times 10 to the negative fifth. Sorry, that's a decimal there. Minus 4.0 times 10 to the negative fourth. X is equal to x squared. So now I have distributed, but I need to, so remember, for quadratic equation, what you need is you need an expression that is 0 equals x squared, blah, 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 what other terms you have. So now I need to rearrange this equation, and I'm just going to come right up to here. And I'm going to say 0 equals x squared. So I'm going to bring this term over to, sorry, I'll bring the x term over to the right first, just so I have it in the correct order. 4.0 times 10 to the negative fourth x. And then this term becomes a negative. So I did kind of blast through a lot of algebra there pretty quickly, just because I want to try and focus on the chemistry as much as possible. Now, at this point, you've got a couple options. You can use your quadratic equation, or if you've got a programmable calculator, I do recommend programming in the quadratic equation in your calculator. It's really not that difficult. You can Google it. Google will tell you how to do that. That's how I do it. I just have the quadratic equation in my calculator. So what I have to do is I just have to put in my value for A, B, and C, and then Google returns the roots for the quadratic equation. So when I had my calculator run the quadratic equation, of course, it gave me 2 roots because x squared, I have 2 roots, and I have 2 possibilities for x, 874, or negative 0. Sorry, too many decimal. That should be a negative, not a decimal. 00914. Okay. So, and this is very typical. You'll have a positive root and a negative root. For this kind of problem, we're never going to have a negative concentration. That does not exist in chemistry. So I know that I can drop my negative root, which means my value for x is my positive root. So now I can keep moving forward. Now I have solved for x, and I know that I have picked the correct root because I'm going to pick the positive one. So let's keep this in the context of the problem itself. What is x again? So we've worked really hard to solve for x, but what is x? So if you go back to your rice table, you can see x is going to end up being the concentration of hydronium ion. This is what we want. It's also the concentration of our nitrite, but that doesn't factor into our pH. So we really want the concentration of hydronium ion. So my concentration of hydronium is equal to my value for x, which means I can now calculate pH, because of course pH is just negative log of hydronium concentration. And so this is going to be negative log of 0.00874. And so when I put that in my calculator, I get a pH of 2.06. This makes sense. We have a weak acid in aqueous solution, so our pH should be acidic. So this is making sense in the context of our problem. Okay. That is step one. Let me just make sure there are no questions here. That is step one. Now we need to go to step two, or the second point in our titration, and that is going to be after 5 milliliters of our potassium hydroxide is added. So I'm going to switch to another sheet because you can see each of these steps takes up quite a bit of space. So I still have the question up here because we're still going to need all of this information. Okay, so at this point, I do have a reaction taking place between an acid and a base, because I still have my sample, my aliquot of weak acid, but now I have added 5 milliliters of my potassium hydroxide. So what I want to do at this point is I want to figure out how many moles of each I have, because my first kind of major step here is to do a stoichiometry problem. And then once I'm done with my stoichiometry problem, then I'll deal with whatever is left over. So let's figure out how many moles of acid we have and how many moles of potassium hydroxide we have. So for our nitrous acid, our sample was 15 milliliters, and of course our concentration is 0.2 molar. So here is our nitrous acid. If I take my concentration and I multiply it by my volume, convert it into liters, so you see I just moved that decimal 3 places to the left, this is going to give me 0.003 moles of my, sorry, I was writing potassium for potassium hydroxide. My brain got a little bit ahead of itself. For my nitrous acid. Okay, so this is how many moles of nitrous acid are in my original sample. Now let's figure out how many moles of potassium hydroxide I added when I added those 5 milliliters. And this is the same kind of calculation because I have my concentration of my potassium hydroxide. Here it is, 0.03 molar. And the volume I've added is 5 milliliters. Again, make sure that you're converting that to liters. And this gives me 0.0015 moles of potassium hydroxide. Okay, so the first thing I have is a stoichiometry problem. I have a weak acid, yes, which can be in equilibrium, but when I react it with a strong base, that base is going to push this reaction forward. So I am going to write my reaction of my weak acid plus my strong base. That is only going to be a forward reaction. It is not going to be in equilibrium. It's going to look like this. So I have my nitrous acid plus my potassium hydroxide is going to give me my salt and water. Again, this is true for, especially if you're dealing with Bronsted-Lowry acids and bases, you're going to generally get a salt and water as your product. Or you can think of these as a double replacement as well. That's another way some people think of this. Okay, so here's my reaction. Again, it is only the forward reaction because that strong base pushes that reaction just in the right direction, and we don't get any left or reverse reaction happening. So I'm going to set my stoichiometry problem up a little bit like a rice table, because I want to know how much is used, how much is left over, and how much I have formed. So I'll show you what that looks like. So I'm going to put my moles of nitrous acid right here, and my moles of potassium hydroxide. And of course I have no moles of my salt, and I don't have to worry about water because that's going to stay constant. Now for my stoichiometry, so usually when we set up a rice table for equilibrium, we would say minus X on the reactant side and plus X on the product side. But in this case, because we only have the forward reaction, I know how much is going to be used. I'm going to use up the number of moles of my limiting reactant. Okay, so which one is limiting here? Well, this is one simple thing about this titration. It is a 1-to-1 ratio. So that means my math is very easy to figure out my limiting reactant. Which one is going to run out first? My potassium hydroxide is going to run out first. So I know what my consumed is, so to speak. If you think of this as a rice table, I am going to use all of my potassium hydroxide, which means this is also a negative 0.0015. And of course, I'm going to form 0.0015 moles of potassium nitrate on that side. And again, just like an equilibrium table, we're just going to add down the column. So 0.003 minus 0.0015, that gives me 0.0015. Of course, my limiting reactant goes to 0. That's exactly what it's supposed to do. And I have, of course, 0.0015 moles of my potassium nitrate. Now you can see the advantage of this table is it really simplifies my calculations, and I know right away how much weak acid I have left over and how much of the salt I have formed. So that's why I like to set these stoichiometry problems up very similar to a rice table, except we're not getting to equilibrium here. We're just doing straight up stoichiometry. Okay, so at this point, my major species in solution are my weak acid, and I have a little bit of salt, but I have no more potassium hydroxide in solution. That is all used up. So what do I have at this point? I've got another equilibrium problem now because I have my weak acid in water, but I've also got some salt with it. So I'm going to, when I do my equilibrium problem, I'm going to have to take into account not only my weak acid, but I'm not starting with 0 moles of my salt. What I need to do first, though, is I need to make sure that I take these moles and change it into concentration. So let's do a little bit of a side calculation. So I need for my equilibrium problem, I'm going to call this my initial concentration of my acid. And that is going to be my number of moles that I have left over the volume of my solution. Okay, this is another place where you have to be careful. So for your volume of solution, remember we started with a 15 milliliter sample of our acid, but we have added more volume. We have added 5 milliliters of base, which means we have a total of 20 milliliters. So this is going to be over 20 milliliters or 0.02 liters. So that's the thing, you need to make sure that you're keeping track of how much volume is in that flask. It's additive. And this gives me a concentration of 0.075 molar. So this is the initial concentration of my weak acid after the stoichiometry is done. I want to do the same thing for my salt, my potassium nitrite. Okay, so we've got our initial concentration of our nitrate, it's going to be the same calculation because we have the same number of moles and we are in the same volume. And so again, we have 0.075 molar of our nitrite salt. Now you might be wondering, why am I calculating this as nitrite instead of potassium nitrate? Potassium is a spectator ion. It does not contribute to our pH at all, so it's not going to change anything. So I'm going to pull it out. And also, you will see, because I have my weak acid and water now, just like I did before, if I write out my expression for equilibrium, I have my hydronium ion plus there's my nitrite. So I already knew ahead of time that I would need the concentration of just nitrite instead of potassium nitrite. So I just went ahead and kind of pushed forward with that and did my concentration. But if you did your concentration of potassium nitrite, it's the same because it's a 1-to-1 ratio. Concentration of potassium nitrite is going to equal your concentration of nitrite. Okay, so now that we have our concentrations, we're going to make a proper rice table. So I already have my reaction. Now for my initial concentrations, which I just calculated. So these just go in 0.075. And don't forget, you do have some nitrite. So you're not starting like we started last time with just your weak acid. This time we have weak acid, but we also have some of its conjugate base. Spoiler, we've got a buffer here. Okay, but we're going to deal with this just as an equilibrium problem. I'm going to use up some amount. Again, this is my consumed. I'm going to form some X here, and I'm going to form some X here. And my equilibrium, I'm just adding down the column again. So this is, oh, sorry. I don't know why I dropped that 5 there, but I dropped that 5. 5 minus X. This one is X, and now this one is 0.075 plus X. Again, it looks a little bit different, but that's because our stoichiometry formed some of that conjugate base. Okay, still pushing forward. So my Ka expression is going to be my concentration of my nitrite. Sorry, that negative didn't come out so well. Hydronium over my nitrous acid. So now I can just plug in for my expression. I'm going to bring this up and over here. Again, I know my Ka, that's still my 4.0 times 10 to the negative 4th. And now again, I'm just taking this equilibrium row and plugging it into the concentrations as they appear in my Ka expression. So this is going to be X for hydronium, and then 0.075 plus X. Oh, I guess I did that backwards. It doesn't matter. I mean, it's all multiplied, so you can put it in whatever order you want. And then this, of course, is over the quantity 0.075 minus X. Okay, so again, ideally, I'd like to drop this plus X and this minus X to simplify my expression, but I have to first run my test calculation and see if I can possibly do that. So I'm going to do this in green. I'm going to have to go on to another page. I just am already running out of space. Okay, so I'm going to take my initial concentration of my acid. I'm going to put it over my Ka, and this should be greater than 500. If it is, then I can drop that minus X and that plus X. So my concentration initially is 0.075, and this is 4.0 times 10 to the negative 4th. Hopefully this is greater than 500. Of course, I've done this calculation, and we get 187. Okay, so that is not right. That's a big no, which means I'm going to have to use quadratic equation again. I'm going to have to do a little bit of algebra first to get it into the correct form, and then I'm going to use the program on my calculator to calculate what my roots are. So let's do a little bit of this algebra, and then I'll switch to another page because I'm just not going to make it here on one page. I was kind of hoping I would, but I'm not going to make it. Okay, so going back to my expression for Ka here, again, just doing some algebra. I'm going to first take my denominator right here and bring it over to the left-hand side. So I'm going to end up having to distribute here. So 5 minus x. And then this side, I'm going to go ahead and distribute this x. So this is 0.075x plus x squared. I'm sorry, I'm getting a little bit squashed here. I'm going to distribute this 4 times 10 to the negative 4th across here. Let's see, what did I get for that? 3.0 times 10 to the negative 5th minus 4.0 times 10 to the negative 4th x. And my right-hand side has stayed the same, plus x squared. Again, for quadratic equation to work, or for putting it in your calculator for the program, we have to get it in the form 0 equals x squared plus something x plus our constant. So we're going to have to do some combining of like terms. So we've got our x squared, that's fine, but we need to combine these two x terms, and then of course my constant term just ends up coming over to the right-hand side. I did do that equation, so this is going to be 0 equals x squared plus 0.0754x minus 3.0 times 10 to the negative 5th. Okay, so now I've got my quadratic in the right form. I can find my roots. Of course, when I run this in my calculator, it's going to give me 2 roots. It's going to give me 3.96 times 10 to the negative 4th, or negative 0.076. Okay, it's not going to be the negative, so my value for x is right here. Okay, let me give myself another page because I need more space. Okay, so I'm just going to carry through, just going to rewrite this. So my value for x is 3.96 times 10 to the negative 4th. But let me come back one page. Remember, we want to keep in mind what is x. We can kind of get lost in doing all that algebra and the quadratic equation. So let's keep in mind what is x. So if I go back to my rice table, I can see again, x is my value for my concentration of hydronium ion. This is exactly what I want to calculate my pH. So this equals my concentration of hydronium ion. And of course, to calculate pH, I'm going to take the negative log of my concentration of hydronium ion, which is going to be negative log of 3.96 times 10 to the negative 4th. So my pH at this point is 3.40. This makes sense. So if you remember from our first step, and I can just slide back here. For our first step, we started with a pH of 2.06. We added base, so our pH ought to go up, but our main species is still our weak acid, so we shouldn't have crossed over neutral yet. So we have a little bit higher pH, but we still have an acidic solution. So again, when you're finished with these calculations, and I know they're long and they're involved, just make sure it makes logical sense in terms of where you are and what your major species are. Okay, are there any questions? No, okay, we have done a lot of calculations, but we're not finished yet. Okay, so that was what I consider step 1 and step 2, and now we have step 3. So at this point, we have added 10 milliliters of our potassium hydroxide. We're going to do the same thing. We want to know what is our pH after 10 milliliters of potassium hydroxide have been added. I'm going back to moles. So for our weak acid, of course, this hasn't changed. I am always going to have 0.003 moles of nitrous acid, because that is what I started with. That is my aliquot. That is my sample. But of course, my moles of potassium hydroxide have changed because now I've added 10 milliliters of potassium hydroxide. So for my potassium hydroxide, my concentration is still, 0.3. now I have added 10 milliliters. So I have 0.003 moles of potassium hydroxide. Okay, so hopefully at this point, just with these moles, you're going, oh, we're at the equivalence point. And yes, we're at the equivalence point. So our moles of acid equal our moles of base. We need to still start with our stoichiometry problem, though. So our acid plus our base gives us our salt and water. So I'm putting moles in. Okay, 0.003 for both of these. I don't have any salt yet. Of course, I'm going to use up 0.003. So you can think of this as, I think some people like to think of this as both are limiting, because you have set it up so that you're using exactly the same number of moles of acid and the same number of moles of base. That means that I end up with 0 moles of my acid and my base. So what do I have in solution? I have my salt. So now I have to deal with my salt in solution. And I know the knee-jerk reaction is to say, oh, well, a salt in solution, your pH is 7. But does this salt have acid-base properties? Yes, it does. Because when I put potassium nitrite in water, of course, I get the potassium cation and the nitrite anion. This is a weak base. Okay, so my potassium, again, is just a spectator ion. It's not going to do anything, but my nitrite does act as a weak base. So I need to take this into account when I calculate my pH. So let's go ahead first and let's get a concentration of nitrite, because we're going to do another equilibrium problem. Okay, so my concentration of nitrite is going to be my moles over my total volume. Again, I have to add my 15 milliliters from my original sample of acid, plus at this point I've added 10 milliliters. Maybe I'll write it like this time. So here is my 15 milliliters plus my 10 milliliters. And this gives me a concentration of 0.12 molar. All right, so now to deal with my equilibrium problem, let's write my rice table. We have nitrite in water. It is going to form a little bit of nitrous acid and a little bit of hydroxide. Okay, so this is why nitrite acts as a weak base. As you can see in water, it's going to protonate a little bit and it's going to leave a little bit of hydroxide. So that's going to bump our pH up a little bit. So we've got our concentration. Again, making my rice table. RICE, my initial concentration here is 0.12. Of course, I don't have any acid left because remember I used it all up, and I don't have any hydroxide. My consumed is just X's across, and then my equilibrium is this. Okay, I don't have a Ka, I have a Kb because this is a reaction of a weak base. So my Kb is going to be my concentration of my nitrous acid times hydroxide over nitrite. Okay, I've got a little bit of a problem. I need a value for Kb. All I have is my Ka for my nitrous acid. So I need to figure out what my Kb is. Yeah, hopefully you have remembered there is an equation to do this. Kw equals Ka times Kb. This is for conjugate pairs. This means if I know my Ka for my nitrous acid, I can figure out my Kb for my nitrite. Now this only works for conjugate pairs. You can't just take a Ka from any acid and say, oh, I'm going to do a Kb for something different. No, they have to be conjugate pairs, and they are related by your Kw or your equilibrium constant for water. So let me run through this calculation, then of course I've got to go to another page. So Kw is 1 times 10 to the negative 14th. My Ka for nitrous acid is 4 times 10 to the negative 4th. And I am solving for Kb. This gives me a Kb of 2.5 times 10 to the negative 11th. Okay, let's go to another page, because again, I'm running out of space. And just rewriting my expression for Kb here. So we've got it HNO2 times hydroxide over NO2. And this equals 2.5 times 10 to the negative 11th. Okay, so plugging in these concentrations right down here, I'm going to switch my 2.5 times 10 to the negative 11th on the left-hand side. That's just kind of where I'm used to having it. And I'm going to get x squared over the quantity 0.12 minus x. Sorry, that decimal is not coming out very well. As always, I really want to drop that minus x if I possibly can. So let me switch colors and let's run our little test where I'm going to take my initial concentration of, in this case, my weak base, and I'm going to put it over its Kb, and hopefully this is greater than 500. Okay, so fingers crossed, right? 0.12 over 2.5 times 10 to the negative 11th. Hopefully this is greater than 500. I'm going to switch right up here. When I do that calculation, I get 4.8 times 10 to the 9th. Yes, that's greater than 500. I'm going to give it a check mark. That means we can drop this minus x. We just totally pull that out. This makes this calculation so much easier. We don't have to do any extra algebra. We're just going to end up doing a square root. It's really nice when you can drop that. So all I'm going to do at this point is I just pull this 0.2 over and take the square root. Like super easy. I get a value of x of 1.73 times 10 to the negative 6. Let's put x back in the context of our problem. So I'm going to switch back to our previous page. So here's our equilibrium. Remember, x is our weak acid, but see, x is our concentration of hydroxide. That is what is key. So this is the concentration of hydroxide. I need to get pH though. So what I'm going to do is I'm going to first calculate pOH and then use my 14 equals pH plus pOH to get to my pH. Again, this is a place, if you're not thinking about putting x back in the context of the problem, you would go ahead and do the negative log thinking that you have the pH, but you've really calculated the pOH. So just make sure, especially when you've got all of this algebra to do, that you keep putting these quantities back in the context of the chemistry, back in the context of the problem itself. Okay, so pOH is negative log of hydroxide, which we have. So I'm just going to do the negative log of 1.73 times 10 to the negative 6. This gives me a pOH of 5.76. Now to find pH, this is simply going to be 14 minus 5.76, and I get a pH of 8.24. All right, so you can see that this is the equivalence point, but when you're titrating a weak acid with a strong base, your equivalence point is not necessarily at a pH of 7. That is true if you've got a strong acid and a strong base, but in our case, we have a weak acid and a strong base, which means we end up with a weak conjugate base in solution at the equivalence point, which is going to push that pH up just a little bit. Now, it depends on the identity of that conjugate base, how much that pH gets pushed up, but you can see that we definitely have a basic solution. We are absolutely above a pH of 7. So that is the equivalence point. We have one more point, and that is after 15 milliliters of potassium hydroxide have been added. Okay, so we're almost there, and I promise this is actually the easiest calculation of them all. And I'll show you why. Okay, so again, I'm going back to moles. I'm going back to moles of my nitrous acid. This has not changed because I started with my sample, and I have not added any more acid. And now for my potassium hydroxide, this has changed. My concentration is still 0.3. But now I have added 15. I have added, yes, that should be 20 milliliters. And this gives me a concentration of, I think I did this calculation wrong. Let me just double check this. 0.3 times, whoops, 20 milliliters. I did 0.006 moles. All right, so this is what we've got. We're again going to do our stoichiometry problem first. So I have my weak acid plus my strong base. And I'm going to get my salt and water. Okay, so this is where I'm going to do my stoichiometry, kind of set up like a rice table, but it's not equilibrium. We're just moving to the right here. So this is 0.003. This is 0.006. Of course, I don't have any of my salt left. This is a limiting reactant, so which one is going to run out first? Which one is going to limit me? In this case, my acid is going to limit me. So I'm going to use up all of my acid. So that is negative 0.003. And this is going to be positive 0.003. So I'm going to make some of my salt. And now I have none of my acid left, but I still have some base left, and I have made some salt. All right, so at this point you're thinking, oh no, but we've made our potassium nitrate. That's a conjugate base. It's a weak base in water. But the thing that's going to really dominate this solution is our potassium hydroxide. So potassium hydroxide, remember, is a strong base. So unless you have an extraordinarily tiny amount, you don't need to worry about your very weak base in water. The other thing that you can think about is if I were to take, well, actually I've written this equation out. Give me just a second. Let's go back. If we think about this equilibrium right here, which is what happens when we have our conjugate base in solution, I have quite a bit of hydroxide now from my potassium hydroxide. That is going to drive the equilibrium back to the left, which means even less of my weak base is creating hydroxide. So again, all of these things work together to make it such that your potassium hydroxide is your major source of hydroxide and the only thing that we need to worry about when we're calculating what is going to be our pOH and then, of course, our pH. I have moles here. So remember, these are all moles because I started with moles up here. So I need to calculate my concentration of hydroxide. I'm kind of skipping a little bit of a step here. Remember, when you have your potassium hydroxide in aqueous solution, it's going to give you potassium and hydroxide. This is a 1-to-1 ratio. So my concentration of potassium hydroxide is equal to my concentration of hydroxide. Now, if you had something like calcium hydroxide, that would not be a 1-to-1 ratio. That would be a 1-to-2 ratio. But again, this is why this problem, at least in this case, we have all 1-to-1 ratios, 1-to-1 of our acid to our base, and also 1-to-1 in terms of the salts of our acid and our base. Okay, so our concentration of hydroxide here is going to be our moles of hydroxide. Remember, this is how many are left, over our total volume. So we started with 15 milliliters. We have added 15 milliliters total. So this is 30 milliliters or 0.30 liters. This is moles. I know I'm going to move this decimal wrong because I always do. So we get a concentration of 0.10 molar. Now remember, you're dealing with hydroxide here, so when we take the negative log, we're calculating pOH. So my pOH is my negative log of my concentration, which is 0.10, which gives me a pOH of 1. And of course, pH equals 14 minus our pOH. So our pH is equal to 13. Let's put this back in the context of our problem. Does it make sense that we have such a high pH? Well, yes, we're past the equivalence point. All we have left in solution is a very strong base. So our pH should be very high. This is a very basic solution. Okay, so that was, I know, a lot. These titration problems are very difficult, especially when you're calculating pH at different points along the titration curve, because sometimes you're taking equilibrium into account, sometimes you've got a conjugate base, sometimes you don't have to mess with equilibrium. So this is really where all of your chemistry knowledge comes into play, because you have to understand how things behave in solution. So is this going to dissolve? What are the ions that are formed? You also have to understand how an acid reacts with a base. You have to bring into account equilibrium, what happens with a weak acid in solution. You have to understand the acid-base properties of different salts so that you can identify weak acids and weak bases that are cations and anions. So it really brings everything together. I hope running through this problem maybe help make it a little more clear to you. And I hope that everybody's finals and midterms goes well. And I will see you guys next time. Bye.